So today we will learn about this visual language models in computer vision. Okay. So nowadays you may know about the ChatGPT, right? So when you write English text, you may heavily depend on the GPT, ChatGPT maybe. Yeah, it's good at translation and question answering and other language-based tasks. Right? So that ChatGPT was originally have some transformer architecture, and originally its architectures are called as GPT-1, and actually we are using GPT-4 now, right? So the paper published in some technical report, the archive, is describing what GPT is here, right? They used some transformer architecture and trained that architecture using many text data in the unsupervised way. And then they fine-tune this GPT architecture they trained to some downstream tasks in NLP. So that was the GPT. So the first thing they did was pre-training the transformer architecture on unlabeled data. But what they did is this kind of things. So given some other words in the sentence, they estimate the future word. Okay, so this is kind of the self-supervised task. Okay, so given a sentence, we can mask some word in the sentence, and then enforce the transformer architecture to estimate that word, and we can apply some laws for estimating that masked word. Okay, this is the self-supervision, and we can enforce some laws using unlabeled data. Okay, so they first collect a lot of data sets, and for this a lot of unlabeled data, they do this kind of self-supervised learning. Okay, and then they fine-tune their transformer trained on this large-scale data, unlabeled data, to some specific task, okay, using their corresponding ground truths. Okay, so they say this kind of approach make the language model based on the transformer record good accuracy on downstream tasks. Okay, so they first train the transformer architecture using large-scale unlabeled data and fine-tune the architecture on specific tasks using their ground truths. Okay, so this was GPT-1 introduced in this archive paper, and so they insist that the transformer with pre-training is critical for obtaining good performance. So this is the full architecture they are having. Okay, this is the GPT-1. They are performing with full performance. But transformer, if they omit the pre-training, then the performance gap is significant. Okay, so they are saying pre-training on unlabeled data, it can raise the performance. Okay. And this auxiliary laws is not that important, but because this is the full model with the auxiliary LM, and this is the baseline without that part, but their performance is not that different between these two. Okay. More important thing is the pre-training on the unlabeled data. And this is the LSTM, which is the alternative to the transformer. Okay, but this is something frequently used before the transformer. Okay, before the transformer, we used LSTM frequently for the sequence data. Okay, so they compare these two and showing that transformer is better for processing the text. Okay, so the lesson we can learn here is we have to use transformer for processing the sequential data like text. Okay, and the second thing is the pre-training is quite important. Okay, to secure the good performance. Okay, this is two things. And the next thing is they do similar approach. And this architecture is called as BRT, but they also did some self-supervised learning. We already learned this in the self-supervised learning part. Okay. They actually slightly differ the self-supervised learning part by doing this kind of two tasks rather than the tasks like this. Okay, they are similar but are slightly different, and they collect more data actually. So the first task is similarly to previous. They randomly mask out the word in a sentence and enforce the laws to estimate this masked word. Okay, that's the first task, masked language model, language maybe prediction. This is the first task. And the second task is, given these two sentences, this is the first sentence, and this is the second sentence. And we have to estimate if second sentence is the next sentence of this first sentence or not. That's the second task, next sentence prediction. So for example, here, the first sentence and second sentence, they are not originally sequenced. Okay, so we already know that those two sentences were not in the same sequence. So we can label it as not next and enforce the network to estimate that not next. Okay, so this was the two tasks used in the BERT, and they also do some. So they pre-train via self-supervised learning the entire architecture, and they fine-tune on the specific task, the downstream task. Okay. So the concept is similar to GPT-1, but BERT, they record better performance compared to the GPT-1. Okay. So among the large language model, the BERT beat the GPT-1. Okay. That was happened in 2019. Okay. And then GPT-3 appears in Leap's paper in 2020. And compared to GPT-1, GPT-2, and BERT, this paper is saying that GPT-3 is having a lot of more parameters within their architecture. Okay, the architecture itself is transformer, but it has more layers and having more parameters. Okay, so it takes a lot of GPUs to properly train this GPT-3. Okay, and this is some variants of the model. Okay. So, and actually, by enlarging the parameters, they are saying in their title, they are saying that language models are few-shot learners. So given very few samples for unseen tasks, they can generalize well, okay? So by doing the pre-training on large-scale unlabeled data, they are saying that this large-scale architecture become a good few-shot learners. Okay, given very few images as the training data, they can learn that task very fast. That's the few-shot learners. Okay. Okay. So this is the parameters. Different number of parameters. So if their architecture having few parameters. This is already not few, but compared to these parameters, that's quite a few, right? Then this is the y-axis is denoting the accuracy, percentage of accuracy for some tasks. And this is the number of examples in that task we are training on. So if we are given 0 samples for that specific task, it is called as zero shot, okay? And if we are given just 1 sample for new task to train, that is called as one-shot learning. And if we are given few data set, but it's not 0 or 1, then they are called as few-shot learning, okay? So this is maybe 2 to maybe 30 or some very few train if we are given few data set, which is not 1 or 0, then they are called as few-shot learning, okay? For example, 2 to maybe 10 or 30, that's a few, right? So when the parameters of the network is large in scale, then they are saying that the accuracy exponentially grows fast when the data is given, okay? For the zero shot, the performance are similar, right? So for zero shot learning, when the training is not given to specific tasks, even though we have large scale model, their performance is limited. But when given just 1 sample for 1 training sample for the new task, the performance is already very different, okay? And given more data, the performance is different according to their parameters, okay? So by increasing the data, the parameter, the architecture size, that language models are becoming the few-shot learners, okay? That's important lesson from the GPT-3, okay? And they also collect more data set, okay? Very, very large scale data set when training the GPT-3. Okay. And they actually beat the SOTA algorithm. Okay. For example, the BERT and GPT-2, they beat in many tasks. Okay. By increasing the architecture size at the same time, increasing the data. For the training data, they can beat previous language models. Okay, so yeah, you can, if you go here, then you can test GPT-3. And also, we are having GPT-4 actually, and also we are, if we fine-tune the GPT architecture on the chat data set, we can obtain ChatGPT, okay? So that's the thing we are using nowadays, okay? So this is the brief introduction of the language models, okay? So now, yeah, this is quite impressive. So nowadays we are experiencing that the ChatGPT, it is almost like the humans, right? It is very good at doing the chat, okay? So the vision community are gradually trying to involve this text representation in their tasks. Okay, for example, this clip is quite a sensational paper in vision domain. So when you are interested in, then please refer this paper for details. Okay, I will explain only the high-level concepts. Okay, so actually, what they can I think the most important part of this clip is they can achieve this zero-shot prediction, okay? So in original image classification application, we have to, for example, train the model using 10 classes, okay? If we train our model using 10 classes, then our model can predict only that 10 classes, okay? This is the normal image classification task, okay? This is the test. But the thing that this clip can achieve is the model can test on some new classes without any training, okay? So we already learned about the continual learning, which can extend the output of the model towards the new class, okay? And we have to train that model, right? Using the new data set. But in zero shot, it is zero shot because we are given zero trained data set for new task, okay? So even without any training data for the new task, we have to estimate that class at the testing. So that's the zero shot, okay? And if we are given one or a few data for new task, it is called as one shot or few shot learning, okay? So anyway, the important characteristics of the clip is that it can achieve zero shot learning, okay? So I will explain how it can achieve this. So the left part is the training stage, and the right part is the testing stage, okay? So in the left, we will perform the contrastive pre-training. Anyways, we will do some pre-training using some large-scale data, okay? But this time, the data itself had to be image and text pairs, okay? So as you know, the GPT was developed by OpenAI, and this clip is also developed by OpenAI. Okay, they collect a lot of image and text pairs. They collect a lot of these image and text pairs. So text is located here, and image are located here. Okay, and they developed the text encoder. This is actually the transformer. They use transformer to encode the text, okay? And also they involve ResNet or transformer architecture for image encoder, okay? And what they did is, so there are n batches, n number of images are in a batch, right, during the training. Then we first get some n number of image features, okay, from this image encoder, right? And we will get n number of text encodings from the n number of texts, okay? And then what we do is we dot product this image with n number of text features, okay? That's actually located here, dot product. By doing dot product, we can get some similarity between these two features, okay? If the dot producted value, that's the scalar, is high, we can say they are similar. And if this dot producted value is low, then small, then we can say their similarity are low, okay? Anyway, we get this n square number of dot product values, okay? And they are denoting the similarity. And actually, this is the first data text description, and this is the first data's image feature, right? So we have to enforce the ground truth value to be the highest as the similarity, okay? So even though we get n square number of similarity, we enforce the similarity is n similarities in the diagonal to be high and suppress all others. Okay. We suppress all others and highlight the similarities in here. So that's the thing we do during the training. Okay. So actually, given image and text pairs, we calculate their similarity and enforce the high similarity between ground truths and suppressing all others. That's the thing happened during the clip training. Okay, so we are actually enforcing the relationship between image and text. Okay, and then in testing, what we do is kind of simple. So here we use the image encoder and text encoder again. And for image, we apply image encoder and get some feature vector. Okay, this image encoder and text encoders are trained in this way. Okay, trained in this way, and we use that to extract the image feature, and also for the text encoder, we will get some features from some text denoting some classes we want to confirm if this this word could be some class name of 10 classes, for example, we used during the training, or some new class name. Okay, this text label, the text word, which is inputted to this text encoder, can be any text. Okay, can be the text which was seen, can be the text which is the class name of the data which was seen during the training. At the same time, the word here could be the some arbitrary text, which was unseen during the training. Okay. Anyways, we input some word to the text encoder and get some text feature here. Okay, and then we can compare these text features with the image feature and measure their similarity via this dot product. Okay, and we choose best one here. We choose one word that have the highest similarity with the image feature. Okay, for example, here we input dog as word, and the dog was encoded as the feature here, right? If it exhibits the highest similarity with the image feature, then it is anyway selected, and we can say this image has the high probability to have the dog. Okay, so even though this dog was not the class which was seen during the training, we can input that dog here to the text encoder, and if the similarity between this encoded text feature and image features are highest, then we will say this image would have that word inside. Okay, so in this way, even though some word which was not seen during the training can be outputted. Okay, so in that sense, we can achieve the zero shot prediction using the claim. Okay, so are you guys following this? Okay, this is important concept. So 한국말로 잠깐만요. I will do some summarization in Korean. Sorry for foreigners. 이거 트레이닝에는 텍스트랑 이미지 페어가 많은데 텍스트 인코더로 뭔가 배치해 있는 n 샘플에 대해서 텍스트 피처 구하고, 이미지에 대해서도 이미지 인코더로 뭔가 이미지 피처를 n 개를 구한 다음에 걔네 정답만 하이라이트하고 나머지 다 서프레스 하도록 뭔가 이미지랑 텍스트 사이에 관계를 학습에서는 이렇게 학습을 하고요. 그 다음에 테스트 때는 그렇게 구해진 이미지 인코더랑 텍스트 인코더로 이미지를 먼저 피처를 구하고 텍스트는 이제 뭐 학습 때 쓰였던 클래스 네임이 올 수도 있고 아니면 새로운 클래스 이름이 막 올 수도 있는 거예요. 그래서 테스트에서 어쨌든 그 학습 때 보여지지 않았던 워드지만 그 워드에 대한 게 텍스트 인코더로 써가지고 뭔가 피처 디스크립션이 됐을 때 이 이미지 피처와 비교를 해서 가장 크다고 생각이 되면 이제 이 영상은 그 클래스를 가졌구나라고 하게 될 수 있어서 이제 학습이 굳이 필요 없는 거죠. 새로운 클래스에 대해서. Anyways, I will continue. Okay, say and also I will further explain what's going on for the training part. So here we actually highlight this diagonal component and suppressing others by applying some cross-entropy laws, okay, twice. In this direction, we apply cross-entropy laws, and then in this direction, we apply the cross-entropy laws, okay? So actually that's denoted here. So we have image encoder and text encoder. We apply image I and text T to image encoder and text encoder and get some image feature and text feature, okay? And we normalize them, okay? And we do dot producting these two vector and multiply some weight. Scalar, this is some scalar value. Okay, this is some diagonal, this is some array, n by n array. We can get it from here, right? And we apply two cross-entropy laws for the verticals and the horizontals, okay? This is denoting their axis, right? So, and we average to these two laws, okay, and do some backward, okay? This is the way we train this clip. Okay, so we apply cross-entropy laws for this direction first, for all of this law, and then we apply cross-entropy for these columns, and averaging these two losses, we update our parameters. Okay, that's happening during the training step of the clip. So the paper collect a lot of image and text pairs, which is actually 400 million. And they use ResNet or VIT, which is the Vision transformer. For the image encoder, they use either of ResNet or VIT, and text encoder, they use the transformer. Okay, using this architecture and collecting large amount of image and text pairs and doing this kind of training, they train the architectures, okay? And they can do testing for the zero shot application using this method, okay? That's the clip. So, okay. So this is some interesting result of the clip. Okay, so this is an interesting graph. So this is y-axis is denoting the maybe zero shot accuracy, and this is the ImageNet performance. Okay, the clip are denoted as star, and all other algorithms are denoted as some other symbols. Okay, so normally the in-data performance are better than transport performance. That's normal in other algorithms, but for the clip, they are almost similar. Their in-domain data performance and the zero-shot performance, they are almost same in clip. Okay, by aligning image features to the text features, they can get some generalization ability. Okay, So seeing this graph, we can conclude that. And so this is the, the performance based on different architectures. So CLIP is providing some slightly different architectures. So they have some trade-off between speed and the accuracy. So yeah, this is the graph for that. And I think this is also interesting graph. So the OpenAI researchers, they train their CLIP architecture on multiple data sets, image classification data set. So maybe you know some CIFAR data set already, and Caltech, ImageNet, Pascal. There are MNIST here, right? So if you train your network using ResNet and also using CLIP on this data set, this is denoting that for Stanford cars, CLIP performs better than ResNet by this amount of percentage. Okay, so this is denoting that CLIP is beating ResNet trained in the supervised way on Stanford car dataset. Okay, so here is the list of the dataset where the CLIP outperforms the ResNet, which is trained in the supervised way. But for some of the data, the CLIP is producing less performance than the ResNet. Okay, but this could be excused because CLIP was trained in the, different way, not with the full supervision, okay, on the data set. And this is the actually the few shot graph. So this is the number of training examples per new class. So this, if we are given 0 training data, then that is 0 shot. And this is 1 shot, and this is the few shot, okay? Anyway, if we are given more data, then the CLIP is exhibiting better performance, okay? And still is better than other competitors, okay? This is the graph. So the thing we can observe here is CLIP is quite a good generalizer, okay? And this is also interesting result. So this is the normal ImageNet images, okay? And this is somehow different style ImageNet dataset. So this is having the images in the cartoon style, right? And also this is the images having the sketch style, okay? Having some different styles, right? Then if you train your ImageNet data using the ResNet architecture, and if you test it on this data, testing data having different styles, like the cartoon or sketch, then their performance decreased a lot. Because of the difference in the styles of the image, you can observe that your model trained on the ImageNet suffers for testing these different style images, okay? But interestingly, the CLIP is good at generalizing its performance on different style testing data, okay? So this is also very good characteristics of the CLIP, okay? So this is the average maybe performance for subsampled ImageNet testing data, and this is the distribution shifted data set, their performance. Okay, so this purple line is showing that the CLIP's performance, and it's almost like this straight line, which is y is equal to x. Okay, CLIP exhibiting the similar performance for the original trained data and domain shifted data. Okay, but this is the traditional networks that was trained on the ImageNet, they suffers for this domain shifted data set. Okay, so this is also the good characteristics in CLIP. And also, this is some weakness of the CLIP, but rather than this weakness, I want to enforce the strengths of the CLIP. So this it's good at zero-shot tasks, but weakness is, of course, zero-shot performance is below the SOTA algorithm, but in some of the cases, they even beat the state-of-the-art algorithm without training on that distributed data. Okay, and it's also weak on some abstract tasks. Okay, and for some of data, it suffers from the zero-shot tasks. For some of zero-shot tasks, it suffers. Okay, and it is susceptible to some adversarial attacks. Okay, and because it is trained by some image text pairs collected from the web, so it suffers from some social bias. Okay. Anyway, this is the CLIP. So we are frequently use actually this text encoder, okay, of the CLIP. You will see soon. Okay. Okay. And then this is the region CLIP. The paper is published in CVPR 22, and their paper name is region CLIP. So we already learned about CLIP. Okay. The CLIP was published in ICML 21. Okay. After this CLIP, some people are extending this CLIP towards the actually object detection task. Okay. So CLIP was the experiments used for CLIP was all classification data. So CLIP encodes the whole images as the feature, right? This ResNet or VIT, they encode whole images as the feature, right? So whole images are inputted to the image encoder. But what this region CLIP does is they input some whole image, but they want to measure the similarity between some regions of the images with the text. Okay. So for example, here, inside the image, there are multiple objects, right? And the entire image has the text descriptions like this. A boy is flying a kite. But for individual boxes, we may have to redesign the text prompt like this. The photo of one cruise, or a photo of a bike, or photo of a boy. Okay, and the aim of this paper is to align the text description and the regions of the images. Okay, and actually, what they report is if they use some object proposal algorithms, so like the selective search, we can get some bounding boxes, okay? And then we can apply the standard CLIP on these images, right? The extract from the object proposal, we can apply CLIP, okay? And if we try to align these regions with the text prompt, then this paper reported that their performance is very low. So for the entire image, the CLIP can align the text and whole image with this amount of accuracy. But if they crop the image into the multiple object and if they try to align the region and text, then their performance is very low. Okay, so this paper try to propose some component that can align region and text, okay, instead of the whole image and text. Okay, so this is what before that I have to explain this. This is the L denote the text encoder of the original clip. Okay, and this VT is denoting the image encoder of the clip. Okay, this T is denoting some teacher maybe. Okay, and this V, just V, is the image encoder we aiming to train. Okay, ideally this have to be some regional image encoder. Okay, this VT is some image encoder, but V becomes the regional image encoder. Okay, and L, this is the text encoder. Okay, so the first step is they anyway secure the clip. Okay, so they generate a lot of image descriptions as the text prompt, and also extract some image pairs. And anyway, they align rank the text encoder and the image encoder, right? Anyway, they secure this clip encoder and clip text encoder. Okay, and then they, for some of the descriptions, they extract this type of descriptions for the knowns. Okay, so for example, here there are boy, and here there are boss. Okay, here there are boss. So from the descriptions, you have to extract some regional descriptions. Okay, and also for that, from the object selective search, some object proposal algorithms, like the selective search algorithm, which was used for the fast CNN, you can generate some image regions as well, right? And this time, this image encoder is regional image encoder we want to train, okay? And this is the same text encoder here. And we will now align this regional image encoder and the text descriptions, okay? Okay. And this is some transfer learning modules. So when you do this, you replace the image feature part of the some object detector using this clip encoder and train further for the object detection task. Okay, that's here, transfer learning for detection. So, I mean, you first secure the clip encoder and the text encoder, and by generating some object proposals and making some known-wise text prompt, you further train the regional image encoder here, right? And then using that image, regional image encoder, you can replace the image extractor part of the object detection algorithm and further train them for the object detection. So that's proposed here, okay? Okay, so this is some result. So for these regions, there are two regions, this region and this region. So actually for the regions, they use the ground truth boxes, okay? For this region and this region, original clip is saying that this region is having umbrella with the probability of 16, Okay, but this region clip can say that this region have the umbrella with the high probability. Okay, so other results are similar, right? This probability is 51. This probability is 37, like that. This is higher than this. Okay, this is slightly less. Okay, anyway. So the regional description, this region clip is better than the clip. Okay. And this is also similar, top 3 result. Okay, so this is the teddy bear with the highest probability 4 hours, but clip, their top 3 result is not very related to this image. Okay, ours, the chocolate cake is highest, but clip is doing that maybe in the wrong way. Okay, and this is also failure case from the region clip. Okay, some cases the region clip still fails. Okay. Okay, and another similar work is the GLIP. So ground language pre-training. So this is also the similar approach to region clip. So the motivation of region clip and GLIP both are extending the clip towards the object detection task. Okay, but they are doing the similar thing, but their approach is slightly different. Okay, so they want to generate some object masks. This is their text prompt. So their text prompt is some sentence. So in clip or region clip, they rather use some word, okay, word. But in GLIP, their text prompt is some sentence, okay? And from this sentence, they want to generate bounding boxes which are related to some word in the sentence, okay? So this is also similar result. From given this sentence, the GLIP find the bounding box which is related to the words, okay? And what they do is they use the clips text encoder here for encoding the prompt, sentence prompt. And they find this type of object proposals, okay, initially using some selective search algorithm, the RPN. This is some network, differentiable network. The selective search that is not differentiable component, using some clustering, by applying some clustering algorithm, they can generate this kind of object proposals, but RPN is trainable component. Okay. Anyways, using the RPN, they first extract this type of useful object, and then they encode their sub-regions using visual encoder they want to train. And then they align this text prompt, their sub-features and sub-regions feature, okay? Actually, their prompt is given as sentence, but they tokenize them like this, all woman and some words here, right? They tokenize them and extract the features of the text here, and similar to clip, they align the text and object proposals, okay? The sentence, the text features of their sentence prompt and the object proposal regions, they align them using similar contrastive learning. And also they apply localization laws for this RPN, okay? So they want to detect the, anyway, further learn this RPN to capture proper object, okay? So this is the alignment used and localization laws here. And by doing this, they can they can achieve this type of application. Okay, this is similar to object detection, but called as grounding, object grounding. They are called as object grounding. Okay. Anyways, this belief is some paper like this. So anyway, the goal is similar. They want to extend the CLIP's ability towards the capturing the regions. Okay, and they can achieve some zero shot by inherently they can achieve zero shot learning. So even though in the sentence it has the word which is unseen during the training, they can capture that part during the testing. Okay. Anyway, they can achieve this zero shot. And another thing I want to share is the grounding deno, which is introduced in a technical paper archive this year. Okay, actually, this paper, their title is quite interesting. So we learned about DINO, which is the state-of-the-art object detection algorithm based on the transformer. Okay, so DETR. This is the DETR-like object detection algorithm, and they're in their title, they are saying they will marry this DINO with the grounded pre-training. Okay, so anyway, that is this task, right? Okay, so for open set object detection, so this means open set object detection means the zero shot task. Okay, even though for unseen classes during the training, they want to perform the object detection. Okay, that's the open set object detection. And another thing you have to see here is this is the closed set object detection we usually perform. Okay, this is what DINO records the SOTA. Okay, but here the thing is open set object detection. So this is ear, lion, bench. The example classes which were unseen during the maybe training, okay? But even unseen during training, they can achieve the object detection. That's the actually zero shot task, okay? And also what they aiming to do is this. So the left lion or bottom man with his head of referring object, his head on, I don't know. Anyway, for some text prompt describing attribute of object, they can anyway reflect that attribute as well when performing the object detection. Okay, when capturing this bounding box, they can not, not only reflect their class name, but wanting further input the attribute during the bounding box search in their object detection pipeline. That's what this grounding DINO wanting to achieve. Okay, and this is actually their pipeline. Okay, so okay, okay. This is the overall model, and this is some sub model. Okay, so here again there are text stream and the image stream. Okay, here the text backbone is clip encoder. The clip's text encoder located here, and here is the image encoder. We randomly initialize it and wanting to train this part. Okay, and in the middle we have the feature enhancer. Actually, there are more details for this feature enhancer module here, and what they do is they first extracted the text feature here, right? And they also have image features here, right? And inputting this image feature and text feature, they apply two cross attention to somehow fuse these two heterogeneous features. Okay, that's happen in this feature enhancer module. Okay, so this text feature somehow have the aspect of the image feature, and this image feature have some aspect of the text feature. So that's happening during this feature enhancer. And also the second important part is the language guided query selection. Okay. So for image features, before applying these image features to the Dino, they select the queries guided by the language. Okay. And another module is here cross-modality decoder. So when doing the decoding of the transformer, they also input both image feature and text feature, and doing cross attention operation for these text and images. Okay, and the final output obtained here, but also similarly as clip, some texts are inputted to the text encoder, and they apply some contrastive laws to align these text words with the last responses. Okay. So when doing the testing, they align with the text labels with the features obtained in the last layer and classify the last layer. Okay, according to the text, their similarity. Okay, that's the grounding deno. Okay, so this is some figures showing the previous how we can extend closed set detector towards the open set detector. So by aligning, this is the original pipeline having some image feature extractor and some neck and head. In here, we can estimate the region and also the classification information. But in the middle, to extend the closed set detector to the open set detector, we can align text features in the middle of the responses of this closed set detector. That's the way to extend the closed set detector to the open set detector. Okay. And there are several open set detector available till now. Grounding deno, this is the state of the art. But here is region clip, and here is grid we saw today. Okay. They have some limited characteristics. Okay. But this grounding deno have the best characteristics. Okay. So we will actually continue this part next class. Okay. So let's finish today's class here. Okay, thank you.